Okay, in this video we're going to talk about network. And you should remember that the word net means total, so we're really just talking about total work. On the agenda we'll look at network. I'll do an example for you guys, and then we'll talk about the connection between net force and network, because there's a really helpful connection there. So the goals here are to calculate network on an object. And so that's looking at just one object, all the different forces on there, and then we'll look at connecting net force and network. So first, network, like I said, it's really just the total amount of work. That word net means total, so anytime you see that, it's really just saying total. So we're basically just looking at calculating the work done by each force separately, and then we're going to add those all up. So if you have 4 different forces on an object, you'll calculate the work done by each, add all of them up, and then that's how you get your network. So a quick example here, I've got an 11 kilogram bucket that's being pulled upward by a 375 Newton force, and I want to find the total work done on the bucket. So let's start with a free body diagram. So I've got the force of gravity pulling down, and I've got that force pulling up. And I'm just going to find the work done by each. Well, if it's being pulled upwards, that's important now because the direction is going to determine the sign of my work. So I'm going to put off to the side here that the displacement is upwards. And so what that's going to tell me is that the force up top here is in the same direction, so it's going to do positive work, and then gravity is going to do negative work. So the net work, first I'm going to determine the work done by each one. So the work done by this applied force is going to come back to that F parallel D, and it's exactly parallel. Oh, and once again, I do this a lot. Let's say that it's pulled, I forgot to give you D, it's pulled 3 meters, just to make things easy. So it's exactly parallel, and so I'm going to have the force of 375 newtons times 3. Let me get my calculator here. So the work done then is 1,125 joules. So there's the first bit. And then I'll find the work done by gravity. And so that's again going to be F parallel D, where this one, the force is exactly opposite. And so it's going to be equal to the force of gravity, which is mass times gravity, times the distance. And then I'm going to fill those in. So 11 kilograms times gravity is 9.8 times the distance of 3 meters. Excuse me.
Bless you.
Thank you. So there I get it's a nice guest appearance by Maggie Hart in this video. So the work done by gravity then is going to be 323.4 joules. So there is the other bit. And I need to acknowledge that since the force there was opposing the motion, that work is negative. And so now when I go to find the network, I'm just going to say that it's the work done by each one added together. So it's the work done by the applied force plus the work done by gravity. And then I just plug in my numbers. So 1,125, and then I'm adding a negative here. So let's just be careful and go ahead and put it in that way. Minus 323.4, and we're going to let our calculator do that. And what we end up with is that the network is going to be 801.6 joules. So all in all, not too bad. It's a little bit lengthy, but not too bad. So we're just finding the work done by each force and then adding them together. Now there's an important connection here between net work and net force that I just want to point out because it can be really powerful, and then I'll give you an example of why it can be really powerful. So one perspective we can take is that the net work is going to be equal to the work done by one force plus the work done by a second force plus all the way up to, n forces. Well, for each one of those forces, for each one of those works, what I'm really doing then is I'm separately saying, well, this is, force 1 times that displacement plus force 2 times that displacement plus all the way up to force n times that displacement. And you could see this in the previous question, right? The displacement was 3 in each one. And so if I look here, I've got the same displacement in every term. And so what I could do is I could factor that out. And so then if I take the d away here, I'm left with f1. If I take it away there, I'm left with f2. And then yada, 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 all the way up to, if I take it away here, fn. And then I have the d there. So this f1 plus f2 plus all the way to fn, well, that is finding the sum of the forces, or in other words, the net force. And so what this tells me is that the net work is equal to the net force multiplied by the displacement. And so this gives us two equally valid ways to find net work. The first one is kind of the classic by the definition way, and the other one is to think about finding the net force first and then multiplying that by d. And you can do that anytime. There are times when using this one will be convenient, and there are times when using this one will be convenient. It just depends on what you're doing. Let me show you an example of when using the net force version is convenient. So here we've got a 45 kilogram box is pulled across a rough surface by a rope horizontal to the ground at constant velocity. And I want to find the net work done by the box. And immediately I notice that once again I failed you by not giving you a displacement. So let's say the displacement here is, I don't know, 7 meters. So one method here would be to go with a free body diagram, right? So we'll start there. We've got a force of gravity going to be on here, and you're going to have a normal force. There's some sort of force pulling it across the surface, and then and it's actually a rope, so let's say it's a tension. And then I've got friction that's opposing that motion. And it's kinetic friction because it's moving. So one method I could do here is I could find the work done by each of these forces individually and then add them all up. But you may be realizing that's a bit complicated and difficult because I actually didn't give you enough information to immediately know the tension. And so you'd have to do like a whole force problem in order to work this out, which is fine. But there's a piece of information here that's extremely helpful, constant velocity. And what we could do now then is say, well, if I'm a constant velocity, that is going to tell me that my acceleration is 0, which should imply then that the net force is also 0. And that's because of Newton's second law. If the acceleration is 0, the net force is 0. And if the net force is 0, then I could use this approach, that the net work is equal to the net force times d. And then I'm just doing a net force of 0 times d of 7. And what I end up with is that the net work is equal to 0 joules. And so that's one way that being able to make this immediate connection here of net work being equal to net force times d, it can keep you from having to do a lot of work. Pun intended. So over here, you could add these all up separately. You could totally do that. That's totally viable, but that problem would then take you 15 minutes to probably work out. If I see this connection, then I can immediately jump here and it becomes a lot easier. So in quick summary, in this video we looked at calculating net work, and we actually looked at two ways to do it. So the first way is we could say that net work is going to be equal to adding up the work done by every force separately. And the other way, which can be more useful at times, is finding first the net force and then multiplying that by the displacement. Both equally valid. Sometimes one is more helpful than the other. And then you've also got this important connection represented in this equation between net force and net work.